Hello and welcome. We are about to embark on a really deep journey into one of the most transformative and, let's be totally honest, one of the most chaotic shifts happening in technology right now: the application of artificial intelligence to our networks and to the edge. And look, if you're feeling like you're trying to drink from a fire hose these days, I want you to know you are absolutely not alone. The pace of innovation in this space, it isn't just fast, it feels exponential. We're talking about foundational models, brand new hardware, entire architectural philosophies that are emerging not just year over year, but it feels like week over week, even day by day. So our goal here, together, is to build a durable mental framework for this entire landscape. We're going to push past the headlines, we're going to cut through the buzzwords, and we're going to build a deep, foundational understanding from the ground up. This is not going to be a surface-level skim. To really get a handle on this, we have to go deep. We need to build a solid structure of knowledge that can actually withstand the constant churn of new developments. So I invite you to settle in because we are going to methodically unpack this piece by piece over an extended time.
So here's the roadmap for our journey. This is the path we're going to take to make sense of it all. We'll start with what we're calling the AI Acceleration Challenge, just to get our arms around the forces that are driving this incredible rapid change. Then, we're going to move into decoding the key buzzwords and the technological shifts that are happening right now. After that, we'll get really practical and talk about architecting for the real world. That's followed by a topic that is completely non-negotiable: security. And we'll wrap up by looking ahead at the collaborative open-source future of this entire domain. So let's get started. Let's begin with the challenge itself.
All right, part one, the AI Acceleration Challenge. And I think the subtitle here just says it all: why it feels like your head is spinning. Because before we can even begin to talk about solutions, we have to really, truly appreciate the nature and the scale of the problem we're facing. This first part's all about establishing a shared understanding of the environment that we're all trying to operate in right now. This quote right here, it gets to the absolute heart of the matter. Because what it is a confession. It's an admission of humility from the very people who are building this future. This tells us that this isn't just about a few new products coming to market. What we're living through is a fundamental paradigm shift, and it's happening at a speed that feels fundamentally different from any of the previous tech cycles we've been through. This sentiment, it validates that feeling of being overwhelmed. It tells all of us that the challenge of simply keeping track is real, it's legitimate, and it's being felt even by industry leaders. This shared experience is our starting point. It's the reason that a methodical, structured approach like the one we're taking today isn't just helpful, it's absolutely essential. It's essential for anyone who's trying to navigate this space, trying to make sound architectural decisions, or even just trying to plan a career path. It's all about building a framework to process what feels like a relentless fire hose of information.
So let's get a little more specific. Let's really break down why our heads are spinning. This slide outlines 3 core drivers, and honestly, each one of these deserves its own deep dive. First up, the rate of AI adoption is accelerating. And I don't mean a gentle curve. We are looking at a near vertical climb. For years, AI and networking was this niche thing, you know? It was about proofs of concept in a lab somewhere. Now it's a strategic imperative that's being discussed in boardrooms. The pressure to adopt is immense. It's driven by this potent combination of FOMO, the fear of being left behind, and the incredible promise of unprecedented efficiency and new revenue. And what this means in practical terms is that projects are being rushed from R&D sandboxes straight into production environments at a truly breakneck pace. Second, and this is a really critical distinction, we're moving from experimentation to true AI-native infrastructure. Experimentation means you're just bolting on an AI feature to a system you already have. It's contained, it's an add-on. AI-native infrastructure, though, that is a complete re-architecture from the ground up. It means you are designing your network, your data pipelines, your hardware procurement, everything, with the core assumption that intelligent, autonomous workloads are the primary citizens of your environment. And the consequences of that shift are profound. It changes how you think about everything, from network bandwidth and data governance to the very skills you need to hire for. It's the difference between, say, adding a supercharger to your family car versus designing a Formula One engine from a blank sheet of paper. They are fundamentally different things. And finally, the real root of the chaos: new breakthroughs are being announced on a weekly and sometimes a daily basis. One week, a new open-source model like Llama 3 comes out and completely changes the performance baseline for everybody. The next week, a new technique like Mixture of Experts comes along and redefines the economic viability of running large models. Then, a new hardware accelerator from a major vendor comes out and promises a 2x performance increase. When the fundamental tools, the very bricks and mortar you're building with, are in a constant state of flux, it makes building stable, long-term systems an incredible challenge.
And this statement, this is the ultimate consequence of that relentless pace we just talked about. You see, in traditional IT and network planning, architects and engineers, we rely on constants. We build on a solid foundation of known quantities. You have a 5-year hardware refresh cycle you can plan around. You have stable, mature networking protocols that don't change overnight. In the world of AI infrastructure, that foundation has turned to quicksand. The best GPU for your workload today
might be obsolete in 18 months. The optimal large language model for your use case could be surpassed by a new open-source release tomorrow morning. The very software framework you choose to build on could be completely disrupted by a new paradigm, like agentic AI. This completely transforms long-range planning from a science into an art form. It demands a totally new approach to architecture, one that values flexibility, modularity, and adaptability above all else. You can no longer build a cathedral designed to last for decades. You have to build a modular base camp that can be constantly reconfigured as the landscape shifts around you.
And this state of constant flux, it forces us to confront a really fundamental strategic question. Which of these new AI capabilities are horizontal, meaning they're general-purpose tools that we can just buy or download off the shelf, and which ones are vertical, requiring deep, domain-specific expertise to build for our unique world of networking and the edge? Let me give you an example. A base language model's ability to summarize a news article, that's a general skill. But can that same model accurately interpret a BGP routing table update? Can it diagnose a complex Kubernetes networking issue just from raw logs? Well, that requires specialized knowledge. That model needs to be trained on domain-specific data, fine-tuned with a very specific vocabulary, and then validated against thousands of real-world network events. Getting this buy versus build decision right is one of the most critical choices an organization is going to make. If you make the wrong call, you could end up wasting millions of dollars trying to reinvent a horizontal wheel. Or, just as bad, you could be trying to hammer a square, general-purpose peg into a round, highly specialized hole.
And that brings us perfectly into part 2. So now that we've established the why, the overwhelming pace of change in the core strategic questions it forces us to ask, we can now turn to the what. This next section is going to be a methodical journey. We're going to walk through the key technologies and concepts that are defining the AI landscape for networking today. We're going to build a clear evolutionary timeline, starting with the absolute simplest ways that enterprises consume AI, and then progressing step by step to the cutting-edge frameworks that are beginning to enable true network autonomy. What you're looking at here is essentially the maturity model for enterprise AI adoption. Think of it as a staircase, and we're going to explore each of these 4 steps in a lot of detail, understanding not just what they are, but more importantly, why the industry progressed from one to the next. You'll see that each stage represents a solution to the limitations of the one that came before it. This progression, it tells the story of how we're moving from simply using AI as a tool to deeply integrating it into the very core of our operations. So let's start at the beginning, the most common entry point for almost everyone, pure API consumption.
The journey for most organizations, it starts right here. Pure API consumption is by far the simplest way to get started with AI. You don't need to be a machine learning expert. You don't need to go out and buy racks of expensive hardware. You simply make a network call to a powerful model that's hosted by a hyperscaler, and you get a result back. The example of contact center modernization is a perfect one. You can stream call audio to an API and, in near real time, get back a full transcript, a concise summary, and a sentiment score. The value is immediate and it's tangible. But, and this is a huge but, this simplicity comes with a really significant trade-off. As soon as you move from these generic tasks to handling sensitive enterprise or customer data, you run headfirst into a massive wall of security, privacy, and regulatory concerns. For industries like telecommunications, finance, or healthcare, setting your proprietary data to a third-party cloud is often a complete non-starter because of data sovereignty laws and privacy commitments. And it was this fundamental limitation that was the primary catalyst for the next major step in our evolutionary path.
The emergence of powerful, high-quality open-source models that could be run locally, that was the absolute game changer. Models coming from organizations like Meta, Mistral, and many others suddenly made it possible for you to have state-of-the-art AI capabilities running inside your own data center, safely behind your own firewall. This immediately solved the problem of data privacy and regulatory compliance. But as it often happens in technology, solving one problem created a brand new, very expensive one: infrastructure. You see, running these models is nothing like running a typical web server. It requires fleets of specialized, power-hungry, and incredibly costly hardware like GPUs. And this introduced a whole new universe of complex economic calculations. All of a sudden, teams had to grapple with massive capital expenditures, or CapEx, for the hardware itself, and then the significant ongoing operational expenditures, or OpEx, for power, for cooling, and for the specialized talent that you need to manage these complex systems. This shift to local models forced the conversation to move from the application layer way down to the fundamental design of the physical infrastructure itself. So after mastering the deployment of local models, the industry is now moving toward a far more sophisticated and powerful paradigm: agentic AI. This is a fundamental shift away from monolithic thinking. Instead of trying to build one giant all-knowing AI model that can do everything, The agentic approach breaks down complex problems into smaller tasks that can be handled by a team of specialized, autonomous agents. The analogy to a microservices architecture is absolutely perfect. Each agent has a single well-defined job. You might have one agent that does nothing but monitor network latency, you might have another that's an expert at analyzing security logs, and a third might know exactly how to reconfigure a firewall. The real power here, the magic, it emerges when these agents collaborate, leveraging external tools and communicating with each other to achieve a complex goal that no single agent could handle on its own. This is the architectural pattern that really begins to unlock true scalable automation.
The language in this quote from Fatih Nar is incredibly precise, and it's really important. By referencing the 12-factor app methodology, he is making a profound point. He's advocating that we treat our AI systems with the same engineering rigor and the same discipline that we apply to our most critical cloud-native applications. The 12-factor principles, things like explicit dependencies, separating your configuration from your code, treating processes as disposable and stateless, these are the things that allow us to build resilient, scalable, and maintainable systems in the cloud. Applying this exact same thinking to AI means moving away from a world of fragile, monolithic Python scripts and toward a robust architecture of independent, scalable agents. This microservices approach is what provides the flexibility and the resilience that you absolutely need for an autonomous system. It's the underlying engineering philosophy that makes genuine autonomy even possible.
So what does this agentic framework actually look like in practice? Well, it's a very clear separation of concerns, and it's broken down into these three distinct roles. First, you have your diagnostic agents. You can think of these as the sensors of the system. Their only job is to observe and collect data. They're monitoring metrics, they're parsing logs, they're watching for alerts. They are the eyes and ears of your system, constantly feeding information into it without making any judgments. Next up are the planning agents. These are the brains of the operation. A planning agent takes in data from all those diagnostic agents, analyzes it, and then formulates a course of action. A key aspect here is its ability to use what we call external toolboxes. This means it's not limited to just its own internal knowledge. It can query databases, it can call other APIs, it can run simulations to help inform its decision. It assesses a situation and then creates a step-by-step plan to resolve it. And finally, you have the execution agents. These are the hands. They take a plan from a planning agent and they interact with the real world to actually carry it out. This could mean reconfiguring a router, scaling a Kubernetes cluster, or blocking a malicious IP address at the firewall. This separation of roles is what makes the system so powerful and so scalable. You can have thousands of simple diagnostic and execution agents being orchestrated by a much smaller number of highly intelligent planning agents.
Now, a system of distributed agents is completely useless if they can't talk to each other. And this brings us to a crucial piece of the puzzle, the need for new protocols that can act as the nervous system for these agentic frameworks. We're starting to see the emergence of standards like MCP and ACP, with more in development. The purpose of these protocols is to create a common language, a lingua franca, for agents to communicate with each other and to interact with their external tools. This is the networking layer for AI. It's what allows a small, lightweight agent that's running on an edge device to securely request a complex analysis from a massive model that's running in a central data center. It's what enables a planning agent to access a proprietary security tool. Without this connective tissue, without this nervous system, the entire distributed microservices-style architecture simply cannot function.
Now, alongside all of these big architectural shifts, there are also major innovations happening within the AI models themselves. And a key one to understand is the mixture of experts, or MO, architecture. In a traditional large language model, the entire massive network of parameters is activated for every single request, which is computationally very, very expensive. MO is a much smarter approach. The model is built from numerous smaller expert subnetworks, and each one of these is specialized in different tasks or different types of knowledge. When a request comes in, a very lightweight routing mechanism directs that request to only the one or two most relevant experts. This means you get the performance and the power of a massive model, but with the inference cost of a much, much smaller one. And this dramatically improves efficiency and reduces the operational cost of running AI at scale.
Okay, so we've now built up our technical vocabulary, we've traced the evolution of AI use from simple APIs all the way to these sophisticated agentic frameworks. And this brings us to the intensely practical challenge that we're going to tackle in Part 3, architecting for the real world. We have all these powerful new capabilities, but where do we physically run them? How do we design an infrastructure that can balance performance, cost, and manageability? We're going to examine the two prevailing philosophies, and then we're going to explore a more nuanced, hybrid solution.
At a very high level, the whole architectural debate really boils down to these two opposing models. The centralized approach involves concentrating all of your AI computing power in one, or maybe a few, very large data centers.
The distributed model, in contrast, pushes those compute resources out into regional sites or even to the far edge of the network. And as you can see from this table, there's a fundamental tension here. The centralized model is optimized for operational simplicity, while the distributed model is optimized for creating business value. And truly understanding this trade-off is the absolute first step in making the right architectural choice for your organization.
This quote perfectly captures the operational perspective. For a site reliability engineer, someone whose entire job is to keep complex systems running smoothly and reliably, the centralized model is a dream come true. Why? Because for an SRE, simplicity and predictability are paramount. Managing a few large, highly standardized data centers is exponentially easier than trying to manage hundreds or even thousands of unique edge locations, each with its own power constraints, its own cooling challenges, and its own networking quirks. Ordering your hardware, your bill of materials, is simpler. Capacity planning is much more straightforward, and troubleshooting is infinitely easier. From a purely operational point of view, centralization reduces complexity and it reduces management overhead, which is why platform engineering teams are so naturally drawn to it.
So if the centralized model is so much easier to manage, why would anyone choose the headache and the complexity of a distributed model? The answer is simple: business value. Pushing your AI capabilities out to the edge, closer to your users and closer to your data sources, unlocks a whole world of new opportunities that are simply impossible in a centralized model. This allows for the creation of entirely new revenue streams, things like real-time AI-powered video analytics in a retail store or ultra-low latency control systems on a factory floor. And there are two key technical benefits that enable this value. The first one is lower latency. For applications like augmented reality or autonomous vehicles, the speed of light delay of a round trip to a distant data center is just unacceptable. And the second is data locality. Processing data right where it's generated is not only faster, but it's often a legal requirement to comply with data sovereignty regulations like GDPR. The distributed model may be operationally harder, but it's often where the real competitive advantage lies.
And this tension, this fundamental conflict between operational simplicity and business value, it leads us to what we're calling the nirvana path. The optimal solution is not an either-or choice. It's not about picking centralized or distributed. It's about an intelligent hybrid model. And this isn't just about finding a lazy compromise in the middle. It's about deliberately designing a tiered infrastructure with a whole spectrum of capabilities, from the massive core to the nimble edge, and then intelligently placing each AI workload in the location that best suits its specific requirements for performance, cost, and data gravity.
This table shows exactly how that workload-aware placement works in practice. The core principle here is to align your investment with your workload's needs. You place your most powerful and your most expensive hardware, your top-tier GPUs and accelerators, in your central data center. This is where you run your most demanding jobs, things like training foundational models from scratch or performing complex, multimodal analysis on video and audio data. Then, in your regional data centers, you can deploy more mid-range hardware, which is perfect for running medium-sized language models that service specific geography. And finally, way out at the edge, where space and power are scarce, you deploy smaller, highly efficient hardware to run lightweight, specialized models that require extremely low latency. This tiered approach allows you to optimize both your performance and your total cost of ownership across your entire infrastructure.
Now, to effectively place those workloads, you first have to understand their characteristics. First, consider volatility. Is the workload predictable, like analyzing a steady stream of network metrics? Or is it highly volatile, like processing a sudden massive burst of logs during a network outage? Predictable loads fit really well in a capacity-planned private data center, while those volatile loads might benefit from the elastic scaling of the public cloud. Next, you need to understand the scaling dimension. Does your workload scale horizontally, meaning you can handle more traffic by just adding more small servers? Or does it scale vertically, where a single task becomes more and more complex and requires a bigger, more powerful server? Then there's context length. For large language models, a longer context requires more memory, which directly impacts your hardware choices and can even drive the need for high-performance networking like RDMA to link GPUs together. And finally, your overall deployment strategy. Whether you absolutely must be on-premise for regulatory reasons, or if you can use a hybrid cloud model to handle bursty traffic, that will ultimately dictate where your workloads are allowed to live.
Okay, we've now architected our applications and our infrastructure, but even the most brilliant, most performant design is completely worthless if it's not secure. And that brings us to part 4, security from day one. The core message here, the thing I really want you to take away, is that security cannot be an afterthought. It can't be something you sprinkle on at the end. It must be a foundational principle that is designed into the system from the very, very beginning.
This quote right here, it powerfully dismantles the outdated checkbox approach to security.
The idea that you can just add a firewall to the network diagram at the end of the design process is dangerously flawed. Sure, it might provide a superficial layer of protection on day one, but it does absolutely nothing to secure the data itself, or the models, or the applications. And on day two, when attackers inevitably find a way past that simple perimeter, the lack of deeply integrated security means you are now facing a much more catastrophic failure. This is a call to action for a holistic security posture that is woven into every single layer of your architecture.
The alternative to just bolting on a firewall is a comprehensive governance framework that secures your data throughout its entire lifecycle. This approach starts with the data. It begins at acquisition, verifying the source and the integrity of your data. It continues through ingestion, securing the pipelines that bring that data into your system. Next up is processing, protecting data while it's actively being used in memory by an AI model. Then comes storage, ensuring your data and your models are encrypted and protected while they're at rest. And finally, we have the two most critical layers for any enterprise use case: controlling access to the data and ensuring that you have the audit and compliance capabilities to prove that your system is secure.
So let's focus on these last two layers for a moment, because they're absolutely critical. Modern access control is so much more sophisticated than simple usernames and passwords. It uses attribute-based controls, which can make decisions based on user roles and data classifications. It can also be context-based, considering factors like the user's physical location or the time of day. The most advanced systems are even moving towards intent-based controls, which seek to understand why the data is being accessed in the first place. And the audit and compliance layer is equally critical. It's not enough to be secure. In the enterprise world, you have to be able to prove it. This layer provides the immutable logs and the reporting capabilities that are necessary to demonstrate compliance to auditors and regulators, which is an absolute, non-negotiable requirement for operating in most enterprise environments.
This entire journey through the challenges, the technologies, the architectures, and the security requirements of AI and networking, it all leads to one very clear conclusion. These problems are simply too large and too complex for any single organization to solve alone. And this brings us to our final part, which shifts our focus from theory to action. We're going to look at how the community is coming together to build an open future through a new collaborative initiative at the Linux Foundation Networking.
The community's answer to these immense challenges is a new, unified open-source project under the Linux Foundation Networking banner. The explicit goal of this project is to accelerate the development and the deployment of AI specifically for the networking domain. This initiative aims to pull the resources and the talent of the entire community to build the common tools, the shared data platforms, and the reference architectures that everyone in the ecosystem can benefit from. It's about preventing the duplication of effort and fostering rapid, collaborative innovation.
This new project is designed to gain immediate momentum by uniting several existing efforts under one roof. It's incorporating work from the Thoth project, which has been focused on the absolutely critical task of anonymizing telco data so that it can be used to train models safely and privately. It's also bringing in the work of the AI Task Force, which has been championing data sharing initiatives across the industry. And critically, it's being kickstarted by a very generous donation of seed code from Infosys, which provides a foundational framework for building AI applications right from day one. By consolidating all these efforts, the project is starting with a really strong base of both technology and community expertise. Any successful open-source project requires transparent and fair governance. The plan here follows a proven, time-tested model. The project will launch with a Transitional Technical Steering Committee, or TSC, that's composed of leaders from the projects that are being merged, and that's to ensure a smooth start. However, following the core principles of the Linux Foundation, the project will move to a fully meritocratic model within 6 to 12 months. And what that means is that the project's leadership will be elected by and from the community of active contributors. This ensures that the project remains neutral and that it's driven by those who are the most invested in its long-term success. This quote right here is the project's call to action, and it emphasizes a really important point, that contributions come in many, many forms. While code is, of course, essential, the project also desperately needs people with operational experience to come in and share real-world use cases. It needs product managers to help define requirements. It needs visionaries to come in and discuss new ideas for technology. It's a truly open invitation for everyone who is wrestling with these challenges to join the effort and help build the solutions that the entire industry needs. And so, after this very deep and comprehensive exploration, we arrive at the ultimate takeaway. We began this journey with a shared feeling of confusion and chaos caused by the relentless pace of AI innovation. We then worked to replace that confusion with clarity by methodically decoding the technologies, the architectures, and the challenges.
And that clarity, I hope, leads us all to an inevitable conclusion. The only path forward is through collaboration. The problems we've discussed are simply too big to solve in silos. The future of AI and networking will be built together, in the open, by the community. I want to leave you with this final thought. We focused heavily today on the technology, but perhaps the most profound shift of all will be a human one. As these autonomous systems take over more and more of the day-to-day, hands-on keyboard operational tasks, the very role of the network engineer will have to evolve. We will move from being reactive operators to being proactive collaborators and strategists. Our job will become less about configuring individual devices and more about teaching, guiding, and setting the strategic goals for these intelligent systems. And this raises a critical question for all of us. How do we prepare ourselves for this new future of human-machine collaboration? That is the challenge and the opportunity that will define the next decade of our careers. Thank you so much for joining me on this deep dive.